Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today we will discuss about classification. So by the word classification we mean it's a task of assigning a known category or class to an object. So consider this particular image, and you can see there are different kinds of objects are present. For example, you can see that say this is the water body, part of the oceans. This is a scene from a sea beach. You can see also the object sun, and there are different spectators or viewers or persons in the sea beach. So one task we can define that whether an object is human or non-human. You can consider any particular rectangular patch of the image, and if it encloses a human, that's mostly the central part of the image. So we may say this is a human object. So similarly, if I consider another patch, you can see that it should be classified into as a non-human part. And in this way, you may define any particular window or any particular rectangular window or patch in the image, and then you can take a decision whether it's a human or non-human. It could be also direction of pedestrian in an image patch where you have a scene of a road, or recognition of an alphabet given a 2D pattern, or assigning a pixel of an image to its foreground or background. So different kinds of classification problems depending upon your requirements from the images we can define. So the way we solve this classification problem, if I look at the processing pipeline, and the input is an input image, and in the system, and as we have already gone through several steps of image processing, we know that this image needs to be processed for making it more convenient for extracting features or extracting information from the images. So those kind of tasks, we call it pre-processing tasks, like noise removal, even the segmentation also, sometimes you can consider it's a part of pre-processing task. Then what you do, we extract features from those objects in the images, or the patches what I mentioned. We have already discussed the feature detection and description in the previous lectures. From there, using those techniques, depending upon the nature of the object, you can derive a representation in the form of, say, feature vector mostly, to represent, or a set of feature vectors to represent an object. So feature extraction modules give you that kind of representation, and then those becomes input to this kind of computational module, which is called classification or computational task, as I was explaining. So from there you have to classify those objects into several classes. I have indicated by different colors by those classes. So it is classified into one of them. Now in this problem, as you can see that we have already identified that what are the classes should be there, and if an object is outside that class, that we cannot handle in this framework. But with this kind of limitations, still we try to solve this problem, and depending upon certain context, this is sufficient to have this kind of few finite number of classes where we would like to classify an objects. So one of the approach for designing this classifier is to learn a model. A classifier is nothing but a model which assigns a class. Through this model, you compute the class assignment given the input in the form of certain representation of the object, say in the form of feature vectors. And the approach, what we usually follow in this learning approach, we call it supervised learning, because what we have in this case, that we have certain number of examples for which we know the class assignments. So those become the input to the model, input to our system, and the system will derive a model based on those input characteristics. So that is the learning part. And then, so that for any unknown object whose class assignment is not known, this model should be able to determine its class. So it exploits knowledge about the classification problem, and such as example instances of classes. That is supervised learning, because somebody is acting like a supervisor to tell, okay, for these examples, these are the classes. So this information is provided from a supervisor. So there are several things which are important when we go for supervised learning. Even the representation of an object in the form of feature vector is very important, because those representation should be able to discriminate classes. So those are the things. Extracting features from images, that is a computational task then, and how well you can do that thing, that is also important. And then from training and test data set with class level. So we have to form this kind of data sets to use this kind of learning. So when you are forming this data set, there the class assignments, class levels are leveled against those feature representation. That's why the extraction of features. And before extraction, you should know that what features you are going to extract, that choice of features. So these are certain stages, certain tasks that is required when you are going to design a classifier. And after, then the next task could be that with those data sets, you have to train the model. So a model is some kind of mathematical abstraction, description is there, where there are certain parameters which are free and which you need to determine during this training process. So for appropriate parameter, it should try to match your input output specifications. So that is the part of training. It should try to match as much as possible. Then we have to evaluate the performance of the model. So not only during training, we should find out how much it could accomplish for the corroboration of the supervised levels, but also there are test data sets, which are the data sets which are not used for training, which are kept for this evaluation. So using test data set as if they are acting like an unknown sample, but we know its class levels, but we have not used it for training. It is meant for only evaluation. Using them, what is the performance of the classifier? So that is more important in this junction. And then after that, when you are satisfied with those performances, then you can use this classifier for any unknown samples, and whatever result comes, you accept it. Definitely, in real scenario, then again some kind of evaluation can tell you how true is your classifier. So mathematically, if I want to describe this classification problem, we can represent in this form, that if we give you a level data set in the form of a couplet like yi, xi, as you can see, and there could be a number of such labeled samples where yi is the level of xi and xi is a feature vector. As you can see, xi is a feature vector and yi is the class of xi, an element of the finite set of classes. So this is how the labels are given, and there are this n could be different. This n could be capital N, because this xi is an n-dimensional feature and this n could be different, capital N. Number of samples is not necessarily should be equal to the dimension of the feature vector. And usually they are different, and usually n is larger than this n is much larger than this n. Okay. So for example, if I consider a feature vector two-dimensional, so let me take a say two-dimensional point as a feature vector, but we can have many such labeled. I am using x1. Let us use x1, x2 as and its label. Say this is the first training sample. Let me use the label. So this is 1. This is a level 1, y1, and we can have such number of sample x1, x2. Say nth sample, and then you can have nth level. So though the dimension is 2, n could be very large. So you can have hundreds of samples, thousands of samples, millions of samples like this. So your objective is that design a classifier C which assigns class yi to xi. That is your objective to solve this problem. For a 2-class problem, usually we have 2 values, and sometimes for the sake of convenience, we take these 2 values as +1 and -1 as a positive classes and negative classes. So, there is no superior, inferior, assignment. It's just a mathematical number that distinguishing 2 classes by these numbers. It doesn't mean positive is better than negative or some reverse. So, typical examples of this problem. Suppose if I give you images of blood sample, determine whether a patient is anemic or not. So, blood samples of a patient, and we have to determine whether the patient is suffering from anemia, the disease anemia, which means their hemoglobin is less than the desired amount of hemoglobin what they should have. So, what we have here, we have the image of the blood sample. So, it's basically a dot of blood, a drop of blood on a tissue paper which has been collected, and then we have taken the image of it. And as you can see, that's a colored image, and the red part is because it's blood is red, so it shows red. And a very simple feature descriptor of the whole sample could be that whichever pixels associated with the blood sample, we consider its color pixels and take the average of red component, green component, and blue component. So, we can summarize the whole sample just by these statistics, say average of red, average of green, and average of blue, which is a feature vector in three-dimensional space. But this is the only feature vector which is representing the sample in this simple representation. And the problem of classifier is that whether the patient is positive, which means whether the patient is anemic. Here the positive class means anemic and negative class means non-anemic. So, this is a classification problem, but it could be also other kind of problem, like given images of blood samples, determine amount of hemoglobin concentration in gram per deciliter. Now, this could be a quantification problem. As you know that from quantification also we can determine whether patient is anemic or not by going through the respective prescribed level of hemoglobin that one should have for a normal subject. So this problem is, instead of classifying into 2 classes, we rather want the quantified value, and we call this kind of problem as regression problem. So, there are different kinds of classification approaches. As we know that classification is a task of assigning a known category or class to an object, and we will be considering 4 typical approaches in this particular lecture. These approaches, what we will be considering, one is probabilistic approach. Say there is a approach based on Bayesian classification rule. So, we will discuss about Bayesian classification. Then it could be distance based approach. So, by considering some of the prototypes, some of the class representatives, we try to find out for an unknown sample which representatives are closer, and there are certain strategies for that. So, the k nearest neighbor is one such algorithm, one such technique which is very popular, which is distance based technique, which we will discuss here. Then discriminant analysis. Here a function will evaluate the classes, right? If there is a linear function and the value of that function, if it is say positive, then we say it's positive class. If it is negative, we say negative class. So this functional form, when it is linear, we call it linear discriminant function, and this analysis, linear discriminant analysis, through which we develop a classifier. And the last one, what we will be discussing, that is on artificial neural network, and which is, as you understand, that widely used for this purpose of classification. And we will typically discuss about a very popular neural network, which is known as feed-forward neural network. So let us first discuss about Bayesian classification, and this classification is based on Bayes' theorem. So let us try to understand what is meant by Bayes' theorem in probability theory, and we will see that what it does by applying this theorem. I will come to the theorem. What we can do, we can predict the probability of an object belonging to a class. So this prediction is there, and there is a simple Bayesian classifier that we will be also discussing, which we call naive Bayesian classifier, where each training example can increase or decrease the probability of the predicted class, and prior knowledge can be combined with observed data in this classification. So let us try to understand this Bayesian inference process or the Bayes theorem. As you know that one particular concept, which is called joint probability, say joint probability of A and B, can be explained in terms of conditional probability. That means probability of A given B or probability of B given A, in this way. So this joint probability of A and B can be considered that A has occurred, then after occurrence of A, B has occurred. So what is the probability of A, and then what is the probability of B given A? Now it is not after, it is basically together there you can consider, but A has occurred, and observing occurrence of A, how do you say what is the probability of B? So that is a conditional probability. So what is the probability? So in the other way also you can say B has occurred, and observing the occurrence of B, what is the probability of A? So this is a conditional probability of A given B. So these two probabilities, if so probability of A multiplied by probability of B given A should give you the joint probability of A and B, or probability of B multiplied by probability of A given B should give you the same. So these two are equated. Now from there we get very interesting relationships of these conditional probabilities. So here you can express the Bayes, this is a Bayes theorem. It looks very simple, but it has a tremendous interpretations, tremendous application in various fields of science. So what it says, let us consider an observation and a hypothesis. So hypothesis here is that belongingness to a class. So this is a hypothesis. So any observation, it belongs to class 1, that is one hypothesis, belongs to class 2, that is another hypothesis, like that. So what we are trying to consider here, that what is the probability of a hypothesis is true given the occurrence of X. So conditional probability of H given X. Now if I apply this relationship considering this joint probability of H and X, so when we apply the relationship as we have shown, that what is the joint probability of H and X together. So probability of conditional probability, that is H given X, should be equal to probability of H multiplied by probability of X given H and divided by probability of X. So I can write those things in this form. Either X has occurred and then we observed what is the probability of this hypothesis is true with that occurrence of X, or we assume that this hypothesis is true, and then what is the probability that X has occurred given that hypothesis. So this relationship from that joint probability distributions has been translated into the form of Bayesian theorem, because what we do in that case, we can take this from here to the denominator and we get this relationship. This is what is your Bayes theorem. So there are certain terms which we should note here. These are technical terms. One thing is that class prior, because H is hypothesis, so what is the prior probability? What is the probability of that hypothesis? That is called prior probability, or the probability of the hypothesis on previous knowledge. So it's something like that. If I consider two persons and ask you that what is the gender of that person, whether male or female. So there is a certain distribution of male and female in a particular, say, community. So prior probability will tell you that without looking at anything, this is the probability that person should be male or female. That is the prior. Already it is there. There is some bias already in the distribution. But of course, based on certain features, again, you want to classify. So this probability is that given that class, what is the probability that it is X? Suppose with some abstract representation of a person, I am giving you the height of the person. So that is the only feature. And by telling the height, you have to tell whether the person is male or female. Okay. So you can have in a particular class, you can have the distribution of the height. So what is the probability of height given the person is male? What is the probability of height given the person is female, for example? So this is called class likelihood, a likelihood function. And then if you want to compute this probability, so this part is called likelihood and this probability of X is called unconditional. This is the basically marginal probability. So if I just say irrespective of male, female, what is the probability of that height? Irrespective of. So you consider all persons irrespective of their gender, you have a distribution of height. What is the probability of this height? So you are computing whether given any, say for example, height that is X, what is the gender or of the person, say whether male or female, right? And then that is called posterior probability. So this part is called posterior probability. So we are computing this posterior because that is our interpretations. If the posterior is high, then we will assign that class. That is the Bayesian rule. So if the probability of given this feature vector, say height, and if given some height, say if we compute that with that height, the probability of being female is this one, and with that height, probability of being male is this one. Now, whichever is higher, we will assign with respect to that person for that height, we will assign that class. Now, this may be wrong also, but these are the probabilities. So, probabilistic interpretation is like that only. It need not be true. There could be error, but we are trying to minimizing that error of classification. The Bayesian classification gives you that certain conditions, it minimizes that kind of error. So, the Bayesian classification rule, as I was mentioning, so given the training data X, posterior probability of a hypothesis, so H, it follows the Bayes theorem. Now, whichever is the highest, assign that class to the highest among all the classes. Whose posterior is highest for all the K classes, you assign that class. So, what are the challenges when you are going to compute? First thing is that you should have a model for computing prior probabilities. Now, this is huge challenge. As I mentioned, I just given an example of, given the height of a person, if you want to predict about the gender of the person. Now, there, first thing you should note that what is the gender distribution in a particular community. Now, you will find in different communities, gender distribution is different, right? That is the prior. So, if certain probability is higher, so it has a higher weightage there. It prior, as you can see, it is in the numerator. Then it tries to find out what is the that class likelihood given that gender distribution. What is the probability of that feature a vector or x. What is the probability of x there? So that is the likelihood. So you can see that it is actually computing joint probability of h and x, but it is divided by the marginal probability of x. Even probability of x is most challenging, which means that now you have to consider all informations. So you have to consider what is the probability of height among all the heights. So you need more information there. Now, one of the thing you can notice here that if x is given, then this denominator part is fixed. So if I consider comparisons between different classes, only numerator plays a role given x. So sometimes what happens, when for the convenience, we may ignore the computation of the posterior probability, precise computation of posterior probability. We may consider some proportional computations. So from proportional computation itself, you get an idea, and then you know that if you know that there are k classes, from that proportional computations, again you can normalize them and you can get the exact posterior probability. So you avoid the computation of or getting the information of probability of x precisely there. So let me once again state the problem statement in this case in the more mathematical form. Suppose your input is a training sample set of tuples and their associated class levels. So each tuple is an n-dimensional vector. Okay, we call them attribute vector. So each position variable, these variables are called attributes, each positions in that vectors. So then if there are m classes C1 to Cm, then you have to derive the maximum posterior, that is the maximal probability of Ci given x, and we can compute in this fashion. And then, as I mentioned, that since this is constant, only this computation is sufficient, and you can use normalizations after that. So this is general Bayesian classifier for general framework for Bayesian classification. When we consider a naive Bayesian classifier, there we simplify these multidimensional conditional distributions formulation. So what actually you have to find out, you consider that here we assume that each attribute is conditionally independent, which means that, say, I have considered a n-dimensional feature vector. So let me write it, then it would be more clear. So we have this n-dimensional feature vector, and I would like to compute the likelihood of the n-dimensional feature vector given a class. Now, if this in the probability description, if all these class conditional, if they are independent, say conditionally independent, then I can simply write them as the product of all individual conditional probabilities for individual attributes. So the interrelationships among the attributes, those are not considered. So it simplifies your expression. It simplifies your expressions, and you can, so you independently you observe the distributions of each attribute in a class, and you can use these simple expressions to compute this multidimensional conditional probability. So that is the advantage you have, and it causes significant reduction of the computational cost. So it requires only the class distributions for each attribute. As you understand, it is convenient to estimate a particular attribute in a single dimension, a particular probability of a particular attribute, and then you simply take the product. And for a categorical or discrete variable also it is simple, because you are considering fraction of times particular value has occurred in a class. That would give you the probability values, And for continuous variable, you can use various continuous distributions like Gaussian distributions, and from there also you can compute these probabilities. So, just to elaborate that part, as I was mentioning, that fractional times for value occurred in a class for categorical discrete variables, or for continuous variable you can use parametric modeling. Like this is a distribution, Gaussian distribution for a single dimensional variable, and you can see there are two parameters, one is mu and another one is sigma. So, to get this distribution, what you need to do the estimation of the parameters. One, you have estimated the parameter, then given any unknown value of x, any arbitrary value of x, that is the attribute value, you can always compute its corresponding probability density value. So, this is how you can consider. Now, that was the probabilistic method for computing posterior probability, and through which you can perform the class assignment. That is the probabilistic approaches for classification. Let us consider the distance based approaches, and where the algorithm, what we will be considering, it is nearest neighbor classification algorithm. The learning algorithm is very simple. What you need to do, you just store the training examples. There is nothing to learn much, only for each class you should have their representative. So, those training examples becomes a representative, and prediction algorithm is that what you need to do, that you find out that which training example is nearest to any unknown feature vector x, and then the class of that training example should be assigned to x. So, this is the nearest neighbor classification rule. So, that is what it does. Now, a bit more improvement on that estimate, because there would be some noise, and if the nearest neighbor itself is noisy, then you will have error in classification. So, to make it more robust, why don't you collect more number of samples which are nearer, which may not be nearest. I mean, rather we can consider a few neighbors which are very close, and then observe their class distribution, and from there you classify the object. So, what we do here in this case, this is called k nearest neighbor method, where k is the hyperparameter. So, it computes the k nearest neighbors. So, nearest neighbor, second nearest neighbor, third nearest neighbor, like that till kth nearest neighbor it computes, and then it finds out that what are the classes for each one and assign that class which occur maximally. So, this is what: examine the k closest training data points to x, assign the object to the most frequently occurring class. So, here is an example. Say you have k nearest neighbor example. So, query pattern for classification, you see that these are the representative samples, and by color I have shown their respective classes. So, you find out the and k is 3. So, you find out what are the distances from each samples, and then choose the nearest 3 classes. So, say for example, you may choose these are the 3 nearest classes, and you have seen here that 2 of them is here say pink. So, you assign the object as the say pink class. So, there are certain probabilistic interpretation for k nearest neighbor also. In fact, in that way it is connected with also Bayesian classification. So, what it does while doing this kind of counting the nearest neighbor, so using that method, effectively what it does non-parametric estimation of probability density at x given k neighbors. So, suppose your number of training samples is n, and assume the volume containing k neighbors is V. So, if the probability of a data point in that volume be P, and following binomial distributions, so a number of data points in that volume could be, expected number of data points in that volume could be n into p equal to k. So, so estimates of the probability that the volume V around X contains a data point is p equal to k by n. And if I consider several classes, for each class you are considering this particular observation. So, probability density function. So, consider a class W1 containing n1 number of neighbors out of k nearest neighbor. So, you have n1 by k, that is the posterior probability of W1 given X. So, this is exactly you are estimating. So, we are not explicitly estimating by doing that computations, but you can have its probabilistic interpretations if we find out what is the number of samples, number of representative samples within that k nearest neighbors. So, that divided by the k will give you an estimate of probability of that class given X, which is called posterior probability, and whichever is highest you are taking. So, that is why the maximally occurring class is assigned. Now, there are some of the issues related to nearest neighbors that we need to understand. First, when you should consider it, when you have the instance map to points in a n-dimensional space, and usually for the sake of computation, we should not take a large multidimensional space. So, thumb rule is that less than 20 attributes per instance should be okay, and also you should have lot of training data so that it becomes more robust. So, the advantage here is that training, it does not require anything, it just storing the data. So, as if that is the training. So, data collection is the major part, and it also learns complex target functions. So, anyway, so I have not discussed with respect to a function. Basically, the kind of class assignment function, that is what is considered the target function. Here the target function is a function which maps a feature point to its corresponding classes. This is a target function. So, this function could be as I was mentioning in the form of say linear function, in the form of linear, but finally you can use a non-linearity after that. We will come to that. So, it could be a simple form, but in the nearest neighbor it is quite complex. You cannot simply express a function in this way. It is a one may consider it's kind of piecewise smooth linear functions, and it do not lose any information. It uses all the training samples, but the problem is that that itself is a problem, because if there are noisy samples, so your decision would be erroneous at certain zones. So, those are disadvantages. It is very slow because it considers all the samples, so computationally very heavy, so slow at query time, and easily fooled by irrelevant attributes, what I was just mentioning, that if there are noisy samples, then you have a problem. Some of the related issues like what distance you should take, mostly you should consider common Euclidean distance. Then choosing the value of k is also important, because if I increase the k, then it reduces the variance, which means it increases the bias or class prior which is dominant. So, which means whichever classes are occurring frequently, if I use a large neighborhood, on the average you will find dominant class is going to be assigned always. So, it is heavily biased to the class bias. So, that's why k should not be very large. So, for high dimensional space, the nearest neighbor may not be close at all. So, that is another problem. For high dimensional space, these distances, they are not reflecting the closeness as it is reflected in low dimensional space. And it is a memory based technique, so it requires lot of storage, and it must make a pass through data points for each classification. So that is why the method is very slow. So, there are certain advanced data structure by which this query could be made efficient, some special data structure, but still the method would be slow. So, it is very much prohibitive for a large data set. So, the next approach what we will be discussing here, that is the based on classification by discriminant functions. So in this case, we consider two class problems in this particular case. I was talking about this target function. So you'll see that we have a function, and that function, there is a certain part of linearity and there is certain part of non-linearity. So you evaluate a linear function, and based on that value, and there is a non-linearity, you assign the class. Say if the value is positive, assign positive class. If value is negative, assign negative class, something like that. So even the assignment could be numeric. You assign +1, you assign -1. It's a symbolic, which means that you are assigning to class 1 or class 2. So here also your input is labeled data sets, as we discussed for the supervisor classification rule. So xi is in the n-dimensional feature space, and yi is in the +1 and -1, and design a discriminant function gx for class assignment. So you see that this is a nonlinearity sign of gx. So you have to design gx such that its sign will give you either +1 or -1. So sign means it is either positive, means +1 or -1. So this is the function you want to design. So we call the decision boundary is the boundary which separates the zones, which separates the zone of samples belonging to positive class and negative class. So if I consider a feature space, and if I consider, say, these are the features, say suppose these are the levels which are positive, say these are the levels which are positive, these are the levels which are negative, right? Same decision boundary may be something like this. So actually the gx equals 0 is the decision boundary, because one side would be positive, gx greater than 0, this is gx less than 0, and this is gx equal to 0. So this is the decision boundary. Now it's a functional form, as you know, it's an analytical functional form, and when this functional form is linear, then we say this is a linear decision boundary. So that's what linear discriminant analysis, we consider G should be in linear form, and if it is a quadratic discriminant analysis, then G should be in the quadratic form. So when G is in linear form, so polynomials of x of degree 1. So that is the case. Suppose you have x is a n-dimensional feature vector. Now let x be represented by this attribute set, n-dimensional set. So a gx can be written as, say, ax1 plus bx2 plus like that, and let me use, say this is a1x1, say this is a2x2, say this is anxn, to use the suffix to denote the differences, and then there is a constant cp. So this is the linear discriminant functional form. Now when you have a quadratic discriminant function, then you have the quadratic terms. So linear terms would be there, but you have terms like, say, x1 square, say x1, x2, x1, x3, like this, x1, xn. So there will be two variables, product of two variables, include a step, and there you are taking its coefficient. Say a11, say this is a12, a13, say this is a1n, plus say a21, which means say x2, x1. I mean, these two could be clubbed together. Like here, we can have only single x1, x2, then a22, x2 square, and like this. So this is the quadratic, and then finally you have also the linear terms. All those linear terms could be also part of this quadratic function, and then you have the coefficient, you have the constant term. So this could be a general form of a quadratic discriminant form. And when the function is in this form, then we call it quadratic discriminant analysis. So you have to design. So you can see that when we are specifying a function, here we are specifying this, we call it coefficients. A1, A2 to An, those are the coefficients. So if I specify those coefficients, this linear function is specified. Similarly, when I specify these coefficients for these quadratic functions, this quadratic function is also specified. So quadratic functions require lot many coefficients than a linear functions that you can see. So designing a function means we have to find out, specify those coefficients only. You have to specify those, get those coefficients which define a function, and then using that function, as you see that you evaluate, given any x, evaluate the value, functional value. If the functional value is positive, then you assign the class level 1. If the functional value is negative, then assign the class level -1. If it is 0, then it is in the boundary. So what decision you take, that depends upon it. So this is what is the classification problem using discriminant function. So if I give you the training samples, labeled data set, how do you get those, how do you derive those appropriate functions which will corroborate to the training data sets as much as possible. So this quadratic discriminant analysis, we say polynomial of x of degree 2, I just explained again. Now, if I consider a base classifier, and there we will see that from base classification expression also we can get also some of this kind of discriminant functions which is in the form of linear or quadratic. Now there we will use the probability density functions, that distributions. We will be use certain known probability density functions, say for example Gaussian distributions. If I use them, then one of the problem I mentioned, that the problem of estimation of those probabilities like posterior probabilities will be reducing to estimation of parameters of those probability distribution. And then when we are estimating those parameters, then whatever analytical expressions you get, those each one, this probabilities itself is a discriminant function. That means the posterior probability, say probability of class Ci given x, it will have an expression. It can be expressed in the form of certain function x. So this becomes your discriminant function. So for class x, this is, I have explained with respect to two classes. So one function was sufficient, but if you have multiple classes, for each class you have a discriminant function, you evaluate them, which one is maximum, you assign the class there. So which means if I will assign the classes, say k, class k should be, or class ck should be argmax that means for the class value, whichever is my maximum, giving me the maximum functional value, which is again the posterior probability. So that functional value should be given as ck. Sometimes this could be just a proportional thing only. It may not be exactly expressing the posterior, but it is expressing certain proportional value. And that's how we can show that in some cases, this discriminant functions, form of this function becomes also linear or quadratic. So this is what now you have to estimate the probability of yi given x. Yi is the respective class identity for all I, and assign the class yk or yk to x, that is a class identity for kth class, if it is maximum. So, difficult to estimate this posterior directly. We have already discussed during Bayesian classification. So, what we do, we estimate prior and estimate the class likelihood. That means we compute the class likelihood and also compute the class prior. And then posterior is computed like this. There is the numerator, and denominator you have the respective marginal probability. And sometimes we may ignore computation of marginal probability, because if x is given to you, so this x, it should be small, as you have seen, not the bigger font, smaller font. So x and since this is same for all the classes, all the yi's in the denominator, so you may ignore that. That is what is meant here. Now, we assume this, when actually we get this kind of linear discriminant function, we assume the likelihood distributions are normal distributions. So, a normal distributions in the multidimensional space can be specified by this. This is the mean vector and this is the covariance matrix. So, Sk for the class kth class. That means there are two classes. For example, if there are two classes, for each class you have its mean vector and its corresponding covariance matrix for the normal vector. So, this is the expression for the normal vector. You can see that here S is the covariance matrix and mean Mk is the mean vector, and you can see that this expression itself is a quadratic expression in the form of matrix. So, so these are the parameters. Mk and S is the parameters here. And this part, no, sometimes we may ignore this part. It's since it's a constant, but it has the corresponding covariance matrix also in the component. So it has certain class dependent properties. So assume covariance matrices are the same. So if I assume covariance matrices are the same, then for different classes also this measure, this term should be the same for the probability. So sometimes we may not use this part to compute the probabilities. So under this condition, when the covariance matrix is same for all the classes, now if I take the logarithm of the probability of class k, that is if I take the respective posterior probability part, so what we find that only from the numerator. So if we can write like this, say probability of class k given x, this is proportional to probability of k, which I am writing here, probability of k into probability of x given class k, which is a normal. So this is a likelihood. Now if I take the log of this, so that would be proportional to log of pk plus log of probability of x given k. And this x given k, when for the kth class, you take the respective parameter, covariance matrix is same. So there, as you can see that I can take also, since I am taking logarithm value, so this part log of c, it relates to this, and this part in the exponential part, exponent of the exponentiation part, if I take the log value, you can simply get these values. So finally, this becomes your discriminant function of x, because these are the parameters, this is a class probability, this is a prior, and this is a constant, and this is the mean vector of a class. This is the covariance matrix which is same for all the classes. So, this is the parameter which is primarily distinguishing the classes. So, we can ignore while comparing this part because this is same for all the classes. And so, finally, this could be reduced into this form. So, we can see that this whole thing can be reduced into this form because we can ignore this one while in comparisons. So, assign class K having maximum value of logarithm value. So, you can see that this looks like a quadratic expression. So, it is a quadratic function because if you have in the matrix form, if you have an expression say x transpose some matrix A x, this is a quadratic form. If I expand it, if I expand this term in the matrix multiplication, you will find that the quadratic terms are occurring, right? So, now let us see how this can be also in a special case can take a linear form. In general, we have seen that is a quadratic form. So, further we will be applying this constraint. Actually, we will be using this rule that S is the same in every class. So, if I expand this, so using simple algebraic manipulations, you can see these are the components. So, you take x transpose S inverse x, then x transpose S inverse mk, then mk transpose S inverse x, so you use a sign, then mk transpose S inverse mk. So this can be reduced to these expressions. And here, what are the terms which are variable with respect to x? This one is with respect to x, it is varying. This is varying with respect to x. This is varying with respect to x. And this is varying with respect to, of course, the class. So, which are the terms which are depending on classes? Now, this one is not depending on classes, class identities. So, but wherever mk is there, those are determining, those are the contributing factor for class comparison, discriminating part. So, we can ignore this part because this part is same for all the classes. So, finally, this expression boils down to this. So, you can see that now it becomes a linear function in terms of x. It is not, so only simply the vector x is coming. There is no quadratic term with the components of the vector x. So, this is a linear form, okay. And as S is symmetric, we can also write this in this form. Yeah, I mean we can reduce, further we can reduce because S is symmetric, then you can combine them and you can write in this form. So, this is the final expression, simplified expression when the covariance matrix is same for all the classes and it becomes a linear discriminant function. So, this is what is the linear discriminant functions. So, with this let me stop here today and we will continue this discussion in the next lecture. Thank you very much for your patience and listening.